Good afternoon, everyone. Welcome to the Marri Laxman Reddy Institute of Technology and Management. This is Kumar, working as an assistant professor for the Department of Electrical and Electronics Engineering. Today, in this lecture series, I'm going to discuss about network analysis. In that network analysis, the particular topic today I'm going to discuss is measurement of active power. Measurement of active power by using two wattmeter method. So this is the one of the method to measure the active power in three-phase circuits. So this is our topic today. So I am going to discuss what is two wattmeter method, how active power is measuring by using two wattmeter method. So here, introduction to a measurement of three-phase active power in three-phase circuits. Three-phase circuits. So generally the active power. So whatever the power we in electrical engineering we are measuring by using a wattmeter. So we are measuring the power by using a wattmeter, a device called a wattmeter. So here it is consisting of a current coil. A wattmeter consists of current coil and voltage coil. So what is the current coil? So current coil is connected in series with the load. So wherever we are measuring the power, so we are connecting the current coil of a wattmeter in series with the load. Whereas the pressure coil or voltage coil of a wattmeter, we are connecting across a lines of a lines of a load. So voltage coil is connected across the supply terminals or across the any two lines to measure the voltage, to sense the voltage. That means that current coil is to measure or to sense the current. It is connected in series with the load, whereas voltage coil or pressure coil is connected across the supply to sense the voltage. So in general, there are three methods are there to measure the active power in a three-phase circuit. One is 1 wattmeter method, second one is 2 wattmeter method, and third one is 3 wattmeter method. These are the three different methods to measure the active power in three-phase circuits. So whatever the load it may be, whether the load is balanced or unbalanced. So these are the three methods to measure the active power in three-phase circuits. So today I am going to discuss in detail about 2 wattmeter method to measure the active power in three-phase circuits. So here I am considering a 2 wattmeter method. For 2 wattmeter method, so here in this method the name indicates the 2 wattmeter method. In this method we are using two wattmeters. Here in this method we are using 2 wattmeters to measure the three-phase power in three-phase circuits. In the three-phase circuits, either it may be a balanced load, the load may be a balanced as well as unbalanced load. That means 2 wattmeter method is used for both balanced load as well as unbalanced loads. In both the loads, we are measuring the three-phase active power in three-phase circuit, active power in three-phase circuits. So in this method, we are using 2 wattmeters. So here in this method, for measuring the active power, so the circuit diagram as shown in figure. So I am considering a star connected load here. Here this is the star connected load. This is circuit diagram for star connected load, and this is the delta connected load. Here we are using 2 wattmeter, wattmeter 1 and wattmeter 2. If you are considering a star connected load, in this star connected load, I am connecting 2 wattmeters W1 and W2. So W1, in this case, W1 is connected in a OR line and whereas W2 wattmeter 2 is connected in Y phase of a three phase balanced load, three phase balanced star connected load. So here current coil CC means current coil is in series with the line, whereas pressure coil or voltage coil PC is nothing but a pressure coil or voltage coil. So here this pressure coil or voltage coil is connected between the line R and B line, line B. And similarly, wattmeter 2, pressure coil of a wattmeter 2 is similarly connected across the supply lines or supply terminal. That is, it is pressure coil PC or voltage coil PC is connected between the Y phase and B phase or Y line and B line. This is the connection diagram for a star connected load. So W1 is the wattmeter reading and W2 is the second wattmeter reading. W1 is the first wattmeter reading and W2 is the reading of a second wattmeter. Whereas here IR, IY and IB. So these are the line currents. So IR is the current flowing through the current coil of a first wattmeter, whereas IY is the current flowing in a current coil of a second wattmeter. So this is the star connected three phase balanced load. So this is a circuit diagram for star connected load to measure the active power by using 2 wattmeter method. So let us consider a delta connected load. So in this delta connected load, the load is connected in delta manner. So the load is connected in a delta manner as usual. So wattmeter 1 is connected in R line and wattmeter 2, second wattmeter is connected in second line, that is Y line. So here also current coil CC is connected in series with the line. In W1 also current coil is connected in series with the line and pressure coil is connected across the supply terminals. So here this pressure coil is connected between R line and B line, and pressure coil of a wattmeter 2 is also connected between the line Y and B line. So that means here the pressure coil of 2 wattmeters are connected, or voltage coil or pressure coil is connected across a supply terminals, whereas current coils of a 2 wattmeters are connected in series with that particular line. So this is circuit diagram for star connected load, star connected balanced load. This is circuit diagram for star connected delta connected balanced load. So this is a circuit diagram in 2 wattmeter methods. So let us consider here. So this is a star connected balanced three phase load. So here W1 is the wattmeter, W1 is the wattmeter 1, reading of a wattmeter 1, W2 is the reading of a wattmeter 2 in Y phase, this is in R phase, whereas IR is the current flowing through a line R, IY is the current or line current flowing through the third phase, that is Y phase. So here VRB is the line voltage, VYB is the line voltage between Y phase and B phase, VRB here. So these are the RB. VRB is the line voltage between R line and B line, and VYB is the line voltage between Y phase and B phase or line Y and B. So this is the voltage across a wattmeter 2. This is the voltage across wattmeter 1. So this is I am considered. Let us consider this particular case where star connected load, star connected balanced load. So here the phasor diagram. So let us see the phasor diagram for a one. As usual, by seeing the circuit diagram, as usual, W1 and W2 are the wattmeter readings. W1 is the wattmeter reading, wattmeter 1. So reading of a wattmeter 1, W2 is the reading of a wattmeter 2. And IR is the current. IR is the current flowing through the current coil of a wattmeter 1, whereas voltage appear across a pressure coil of a wattmeter 1 is V or B. And similarly, the wattmeter reading. So wattmeter reading of a W1. So W1 is equals. So wattmeter measure the power. We know the formula for power. So power is nothing but a voltage into current into cosine angle between. So voltage and current. So here I am writing here. So W1 is the wattmeter reading of a first wattmeter reading. So this is nothing but a power. It measure the power. So what is the formula for power? Voltage. In general, voltage into current into cosine angle between voltage and current. So this is the equation or formula for power equation in general. Here for wattmeter we are connecting across voltage across a R phase and B phase. So this is the voltage. The current flowing through a current coil of a wattmeter 1 is IR, and the voltage angle between cosine angle between VRB and IR. So this is the cosine angle between VRB and IR is a cos phi, and VRB is the voltage across a wattmeter 1. So IR is the current flowing through the wattmeter 1. So this is the power equation. That is nothing but a wattmeter reading of a wattmeter 1. W1 is equals VRB IR cos of angle between VRB and IR. Similarly, the wattmeter reading of a W2. So here also W2 is also measure the power. The power equation is voltage into current into cos phi. So here what is the voltage across second wattmeter? So voltage across second wattmeter is VYB, and current through the second wattmeter is IY, and cosine angle between these voltages VYB and angle between VYB and IY. So this is a power equation. This is nothing but a reading of a wattmeter 2. So next we will consider a phasor diagram. How to draw the phasor diagram? We know that. So I am considering voltage VR, line voltage, VY, VB. So these are the voltages. So here in general in three-phase circuits, so if we are considering VR, VY and VB. So for each and every phase voltage there is a 120 degrees phase displacement from each phase. So VR is 120 degrees away from the VY, VB is away from the 120 degrees away from the VY. Similarly, this is the case 120 degrees each. So like that, so I am considering VR, VY and VB. So we can see the phasors of VR, VY and VB. So here in this phasor diagram, I am considering a lagging load. That is inductive load. For inductive load, the current is, if you are taking a voltage, the current is lagging with respect to the voltage. So if you are considering voltage as a reference, current is lagging with respect to the voltage for inductive load or lagging power factor load. So here this phasor diagram I am consider for lagging power factor load, that is in particularly inductive loads. So here compared to VR, this is the voltage, the line current, this is the line voltage, this is the current. IR is at an angle of phi. Similarly, so current Vy is the voltage, Iy is the current. So current lags voltage by an angle phi. Similarly, so V by, so Vb. Here also the current is lagging. Ib, line current Ib is lagging with respect to voltage Vb with an angle of phi. So this is a lagging power factor load. So this is a phasor diagram. So we know that we need, in order to find the wattmeter reading, for example, if you want to find the wattmeter reading W1, so W1 is nothing but a voltage between RB and current in a line R and cos of voltage angle between VRB and IR. So this is, we need angle between VRB and IR, and similarly voltage VRB. So voltage across R phase and B phase is given by VRN minus VBN. So this is a phase voltage. So if you are extending the voltage VB, so this is V minus VB. So by combining these two, so we can get VRB. VRN minus VBN is nothing but VRB. So what is the angle between VRB and IR? The angle between, so the total angle, the angle between, here you can see, here the angle between VRB and VR is the 30 degrees. Okay, now the angle between VRB and this line voltage and phase voltage, the voltage angle is, the angle between line voltage and phase voltage is 30 degrees. So but we need the angle between, line voltage VRB and line current IR. So this will get, so by 30 minus 5. So this is the angle between VRB and VIR. So finally we can write the reading of a wattmeter reading W1 is equals VRB IR cos of, what is the angle here? 30 minus 5. So this is the total wattmeter reading. In star connected load, we know that, so what we know, what is the relation between phase voltage and line voltage? So phase voltage is given by 1 by root 3 times line voltage. So by taking this, by substituting in this equation, so we are getting root 3 times V phase I phase cos of 30 minus 5. So similarly, phase current is equals line current. Phase current is line current. Phase current is equals line current in star connection. So by substituting in place of phase current, so finally we are getting W1 is equals root 3 times V phase IL cos of 30 minus 5. So this is the final equation. So by substituting in terms of line voltage, so we are getting VL IL cos of 30 minus 5. So let us consider reading of a second wattmeter. The reading of a second wattmeter is given by W2 is equals V phase. Sir, what is the voltage across Y phase and current through Y phase and cosine angle between VYB and IY. So we need what is YB. So YB we can write, VYB we can write it as, so VYN minus VBN. So these are the phase voltage. Difference of these two phase voltages is nothing but a line voltage Vy. So from the phasor diagram, we can see what is the line voltage. What is the line voltage Vyb? So here Vyb. So this is a Vyb. So this is Vyb is nothing but a difference between Vyn minus Vbn. So here this is a Vbn. So this is a Vyn. By combining these two, we are getting V line voltage Vyb. Here we know that the angle between Vyn and In is the power factor angle or lagging angle phi. This is the phi. Whereas the phase voltage and line voltage, the angle between phase Yn and line voltage Yb, the angle between phase voltage and line voltage is the 30 degrees. But we need the voltage angle between Yb and Iy. The angle, the total angle, this is the total angle. We require, this is total angle. The angle between Vyb and line current Iy. So that is nothing but by adding 30 plus 5, we are getting the total angle between line voltage Vyb and line current Iy. So this is the angle between 30 plus 5 is the angle between voltage Vyb and Iy. So finally, by taking the expression of reading of a W2 wattmeter reading, W2 is equals, so W2 I am writing here, W2 is equals voltage Yb, current Iy, cosine of angle between these two is nothing but 30 plus 5. So this is the angle from this phasor diagram. So finally we can write Vyb Iy cos 30 plus 5. So in terms of this line current, in terms of phase current in star connected load, V phase IL cos at an angle of 30 plus 5. So these are the readings of a 2 wattmeters. Wattmeter 1, so this is the wattmeter reading W1. This is the reading of a second wattmeter 2. But we know that the power in a 3-phase circuit, that means the total power in 3-phase circuit is given by here. So we can write the 3-phase power, the total power in 3-phase circuit is given by 3 times the power I phase, V phase, I phase cos phi. So this is in terms of line voltages IL, VL, IL and cos phi. So this is all about the 3-phase power in a 2 wattmeter method. So let us consider or let us add W1 and wattmeter readings W1 and W2. By adding this W1 and W2, W1 is given by root 3 V phase I phase cos 30 minus 5, whereas W2 is the root 3 V phase I phase cos, angle between these two is nothing but a 30 plus 5. So these are the 2 wattmeter reading. By taking root 3 V phase I phase common, cos 30 minus 5 plus cos 30 plus 5. So we know that the formula for trigonometric, from the trigonometric functions, so we can get cos of A minus B plus cos of A plus B. So we are getting 2 cos A and cos B. From that one, 2 into cos 5 cos 30. So root 3 V phase I phase 2 cos 5, whereas cos 30 is the root 3 by 2. This 2 get cancelled. We are getting, so root 3 into root 3. Root 3 into root 3 is nothing but 3. Finally, we are getting, so 3 V phase I phase cos 5. So that means W1 plus W2. W1 plus W2 is equals root 3 times in terms of line voltages. So we can write like this. So this is a W1 plus W2. So we are proved that, so it is proved that the sum of the wattmeter readings is equal to the 3-phase power. So the sum, this is the sum of the 2 wattmeter reading. This wattmeter reading, sum of the 2 wattmeter readings is nothing but a 3-phase power. Power in a 3-phase circuit, that is root 3 VL IL cos phi in terms of line voltages. So this is a power in a 3-phase circuits. Power in a 3-phase circuits. So power in a 3-phase circuits is equal to the sum of 2 wattmeter readings. This way we are measuring the power in a 3-phase circuits. So that means power in a 3-phase circuits is equal to the sum of the 2 wattmeter readings. So this is the way to measure the power by using these 2 wattmeters, W1 and W2. Next, we will see if we are subtracting 2 wattmeter readings. So consider 2 wattmeter readings. So W1 minus W2. If you are subtracting 2 wattmeter readings, so what we will get? Let us see. So W1 minus W2. So we know that W1 is equals root 3 times V phase I phase. So here I am writing. So W1 is equals root 3 V phase I phase cos 30 minus 5 is the W1. So whereas reading of a W2 is equals root 3 times V phase I phase cos at an angle of 30 plus 5. So these are by adding these two one here. So there is a trigonometric consistent cos A minus B minus cos A plus B. By using this formula, we can get cos A cos B, 2 cos A cos B. By this trigonometric identity, so we are getting, by this trigonometric identity, we can write W1 minus W2 is equals cos A minus B minus cos A plus B. So this can write 2 sin A sin B. So by writing this one, so we are getting root 3 times V phase I phase and 2 times sin phi. So where sin 30 is nothing but 1 by 2. So this 2 and this 2 is cancelled. Finally we are getting root 3 V phase I phase sin phi. So this is the final, this is the equation. So here I am multiplying in both sides with root 3. So we are getting, so this one. So multiplying this equation by root 3. Root 3 times W1 minus W2, root 3 into root 3. So root 3 into, in right hand side, root 3 into root 3, we are getting 3. 3 times V phase I phase sin phi. So here root 3 W1 minus W2 by W1 minus W2 is equals root 3 times VL IL. So we know that in star connected load V phase is equals VL by root 3. So in terms of this one, so we can write this root 3 VL IL sin phi. So by dividing in previous equation with previous equation, so we are getting root 3 W1 minus W2 by W1 plus W2. So here these terms are similar, these two are cancelled. So sin by cos is nothing but a tan. So tan phi. So we are getting phi is equals tan inverse root 3 W1 minus W2 by W1 plus W2. Here we know that to find the power factor, we know that power factor is nothing but a cos phi. So by substituting this one, we are getting cos of tan inverse root 3 W1 minus W2 by W1 plus W2. Finally, we are concluded the power factor by using in a 2 wattmeter method. The power factor of a 3-phase circuit by using 2 wattmeter method. And by using 2 wattmeter readings, we can find power factor is equals cos of tan inverse root 3 times W1 wattmeter reading W1 minus W2 by W1 plus W2. So this is derived by considering a lagging power factor loads, that is inductive loads. For lagging power factor loads, that is nothing but a inductive loads, the power factor can be calculated like this: cos of tan inverse root 3 times W1 minus W2 by W1 plus W2. So here for leading, if we are considering the leading power factor load, so in leading power factor loads are nothing but a capacity loads. For capacity loads, the power factor is leading. The leading power factor load, the power factor is given by cos of tan inverse. Here you remember power factor, cos of minus root 3 times W1 minus W2 by W1 plus W2. So this is the difference you need to remember. So for lagging power factor loads, there is no minus sign. So for leading power factor loads, there is a minus term, cos of tan inverse minus of root 3 times W1 minus W2 by W1 plus W2. So we will see, next we will see the effect of change in power factor on wattmeter readings. So for different power factors, so what will be the readings of a W1 and W2 wattmeter readings, W1 and W2. So let us consider 2 wattmeter readings. So we derived previously. So W1 is equals root 3 times V phase I phase cos of 30 minus 5. W2 reading is so root 3 times V phase I phase cos of 30 plus 5. So I am considering unity power factor case. So if we are changing the power factor, what will be the wattmeter readings? So I am considering a unity power factor load. Unity power factor means power factor is nothing but a cos phi. Cos phi is equals to 1. So cos phi is equals to 1, the phi is equals to 0. If I am substituting in W1, so root 3 times V phase I phase, so cos of 30 minus 0. So that is nothing but a root 3 V phase I phase cos 30 we are getting. Similarly, reading of a wattmeter 2. So root 3 V phase I phase, here for unity power factor load phi is 0. So this is also we are getting root 3 V phase I phase cos 30. Here you observe W1 is root 3 V phase I phase cos 30. Similarly, W2 reading of a wattmeter 2 is also root 3 V phase I phase cos 30. That means for both the wattmeter readings are positive. Here for unity power factor load, if you are considering a unity power factor, that is power factor is equals to 1, both wattmeter readings will be positive and the values also equal. So this is the effect of power factor on wattmeter reading when we are considering the power factor is unity. So next Next case, we are considering the power factor is equals 0.5. If power factor is equals 0.5 is nothing but a cos phi is equals to 0.5. Cos phi is equals, the angle phi is equals 60. If you are substituting in place of phi in W1 and W2, so W1 we are getting root 3 times V phase I phase cos 30. W2 is equals root 3 V phase I phase 30 plus this phi. That is nothing but a 30 plus 60. This is 90. So 90. Cos 90 is equals to 0. Here W1 is equals, we are getting some value, root 3 times V phase I phase cos 30, and W2 value is equals to 0. We are getting these two values when we are considering power factor is equals 0.5 with a power factor angle is equals to 6. In that time, the power factor angle is equals to 60, W1 is equals this value, and W2 value is equals to 0. So here the conclusion is, at a power factor equal to 0.5, one of the voltmeter will be given 0 reading. So that is the effect of power factor. That too power factor is equals to 0.5. The one of the voltmeter will be given 0 value. So that is the second observation. Third observation, wattmeter, the power factor which we are consider here is, the power factor is less than 0.5. Less than 0.5. That means angle phi, power factor angle phi is greater than 60. For greater than 60, the W1 is equals to root 3 V phase I phase cos 35, cos 30 minus phi. W2 is equal to root 3 V phase I phase cos 30 plus phi. If power factor cos phi, power factor angle phi greater than 0, W1 will give the positive reading, W2 will give the negative reading. So here phi greater than 60, that is power factor is equals, power factor is less than 0.5, phi is greater than 60 degrees. Greater than 60 degrees, W1, W2 values are, so W1 will be positive value, definitely it is gives positive reading, W2, but W2 is giving negative reading. So that is our observation. The wattmeters will be given a negative reading. So less than 0, power factor is less than 0.5, one of the wattmeter will give negative reading. Next, final last case, when the load is purely inductive and capacitive. So that is the case. I am considering load as a pure inductive and capacitive loads. So here for pure inductive loads, if you are taking voltage as a common, current is lagging in a pure inductive loads by 90 degrees. The phi is equals to 90 degrees. Similarly, capacity load, voltage is taken as a reference, current is leading with respect to voltage by 90 degrees. That means for purely inductive load, the power factor angle, the angle between voltage and current is 90 degrees. If you are substituting phi is equals 90 degrees in W1 reading of a wattmeter 1 and wattmeter 2, we are getting VL cos 60. So if you are substituting phi is equals 90 degrees in W2 reading, so minus VL sin 30. Here we can observe here the wattmeter shows equal but opposite reading. Here we are getting VL cos 60. Here we are getting minus VL sin 30. Hence the total power consumed will be equal to 0. So as we know that for pure inductance, the power consumed by the pure inductive load is 0, whereas the power consumed by the pure capacity load is also 0. Here also, when we are considering a load as a purely inductive or capacitive, the total power consumed by the circuit or load is equals to 0. So these are the four different cases, different changes in power factor. So what will be the readings of a wattmeters? Wattmeter readings, how will be taking values of a power. So here inductive and purely inductive and capacity load for total power consumed by the wattmeters is equals to 0. When the power factor is less than 0.5, that is 5 is greater than 60, the one of the wattmeter reading is negative. So whereas the power factor is equals to 0.5, so the wattmeter reading W2 is equals to 0 and wattmeter 1 is positive value. So whereas in case of power factor is unity, the wattmeter, both the wattmeter reading will be positive and equal. So this is the effect of change in power factor and wattmeter reading in two wattmeter methods to measure the power, three-phase power in a balanced load. So this is all about the measurement of active power in three-phase circuit by using two wattmeter method. So thank you, one and all.